Okay, so this is going to be our second video on circular motion. We watched one at the very end of our kinematics unit where we talked about centripetal acceleration a little bit. And if you have the chance, I would highly suggest going back and rewatching that video. But now that we're talking about circular motion again, we're going to be starting to talk about what it takes to force an object into circular motion. And I already used that word force, which is why it fits inside this unit. So I have three scenarios. We've got a ball rolling, it's been kicked, and I want to know what happens after the kick. In the first scenario, we have the ball rolling to the right and it's kicked downwards, just like a sharp, quick kick. Then we have an object that's rolling to the right and gets kicked backwards. And I want to know, okay, what's going to happen? And then finally, we have an object that's rolling forward and it gets kicked at like a 45-degree angle. So if you want to, pause the video right now and make predictions about what you think the path of the ball will be. Pause now. Okay, great job. So hopefully you said that this object here, while it was going this direction, is now going to go that direction. The force of the kick added some downwards velocity or added some y direction velocity, but it didn't have any effect on the x direction velocity. So it kept rolling to the right, but now it's also rolling down, so we get the diagonal. If I kick it back the same way, some different things could happen. It could slow down, it could stop, or it could go back the other direction, depending on how hard I kick it. Let's just say that it stops in order to set us up for the next one, where if we kick this with the right level of force, it would have been going, it would go like here and then just stops, yeah. Uh, Going like this, and if I kicked it with the same amount of horizontal here and the same amount of vertical here, I would suddenly make it go that direction. And I just created a turn. A turn doesn't come from kicking it from the side because that just makes it change direction but continue going in that straight line. In order to get something to turn, you have to hit it at an angle to get rid of whatever direction it currently has and then give it a new direction for it to have only in that direction. So this force right here, it turns out, is very close to what we might call a centripetal force, especially if we start talking about doing it very slowly. But I want to put this word into the bad word corner because I want you guys to know that it's a word you have to be very careful with. Centripetal means a force that goes towards the center. It's not actually a type of force the way that gravity, normal, and tension are. That means that centripetal force is not a new force that makes things go in circles. It's an existing force that we're describing the direction of. So friction can act in a centripetal direction. Normal force can act in a centripetal direction. Gravity can act in a centripetal direction. There's no such thing as just a centripetal force that makes things move in circles. So that goes in the bad word corner because I need you guys to know that really this is a type of net force, a sum of forces that adds up to be in a centripetal direction. Continuing on, well, let's do some quick demonstrations in my chair here. Let's talk about if we did these three scenarios, but instead of doing it with the ball, we were doing it in a car. So you can imagine that if I was driving, and then I slammed on the gas pedal, I would get pushed backwards. You guys can all imagine that. You've all had that experience. Or if I was at a stoplight and I slammed on the gas, I would feel like I got pushed backwards. But there's nothing there that does that. There's no hand that pushes me backwards. I'm not actually being pushed backwards. There is an apparent force that I think exists but doesn't really exist. What's actually happening is Newton's first law says an object in motion will stay in motion. And so my body's trying to go at a constant speed. But then when somebody slams on the gas or somebody accelerates when we were at stop, suddenly my body is going to try to stay in the same spot. And so I'm staying here, feeling like I'm going backwards, and I get pushed forward by the car and all of the apparatus there. So to me, it feels like I'm being pushed backwards, but really I'm just trying to stay in the same spot because of Newton's first law. There's no force doing that. It just is something that we think exists in our mind because our reference frame makes it seem like the car is stationary when really the car is accelerating and we're being forced to eventually move with the car. The opposite thing happens if you slam on the brakes. When you slam on the brakes, it feels like you are thrown forward. But if you look behind you, you've probably noticed nobody actually throws you forward. What's actually happening is, once again, your body is trying to stay in motion, following Newton's first law, and suddenly you get pulled backwards. You're trying to go forward, and the actual force is the seatbelt and friction and the dashboard or whatever that pushes you backwards. So both of these are examples of apparent forces. The push backwards when you're accelerating, or the push forward when you're slowing down and stopping, seem like they exist, but they're not real forces. The same thing exists with this idea of making turns. That's our second bad word. If I was making a left turn, you guys all know that it would feel like you start moving off to the side. If I'm making a left turn, I go right. But I'm not really going right. What's happening is my body's trying to go in a straight line while the car is going off to the left. So as we diverge, I get the apparent feeling that I'm being pushed to the right because I think that the car is a stationary reference frame. The only thing that actually happens is, eventually, when I hit the door or whatever is off to the side of me, then the real force comes in and pushes me towards the center of that turn and pushes me in a centripetal direction. So centripetal forces are useful when we're describing the direction of forces. But when I hit the side of that door, there's not a new force that just existed called centripetal force. There's the same force that we knew about all last week, normal force, that's now a surface in contact with me that happens to be going in a centripetal direction. The other bad word, though, the one I want you guys to avoid, is centrifugal, which is something that your middle school or elementary school teachers, centrifugal, may have said. They may have talked about a centrifugal force, and that's a bad word. Centrifugal forces do not actually exist in any way. They are just an apparent force that we think pushes us out of objects. So when we're making that turn, people say, oh, centrifugal force is pushing you off to the right. But there's nothing pushing you there. That's just Newton's first law of you trying to go in a straight line while everything else turns. So you should never use the word centrifugal force. And if you see it on a test or on a quiz, you should immediately know that that must be a wrong answer, because there's no such thing at all as a centrifugal force. A centripetal force is okay to use as long as we're using it as a direction. But both of those are bad words if we're trying to use them as the name for the force that's creating the push or the pull. They're not pushes or pulls. Centripetal is just a direction of a push or pull. And I guess I should mention centripetal means center seeking. Centrifugal means center fleeing. You do have centripetal forces. You don't have centrifugal forces, ever. Get it in your heads. Okay. So we have a couple equations that I just want to bring up that you guys already know about. Newton's second law says the sum of the forces over m is equal to the acceleration. And then we have, we talked about this at the end of the kinematics unit, where if we have centripetal acceleration, it would be v squared over r. So we have these two equations, and it turns out that we can merge them if we're trying to talk about the forces involved in circular motion. And when we merge these together, we can set them equal to each other, and we can say that the centripetal acceleration is equal to the sum of the actual forces, the real pushes or pulls, over the mass. So this is a very useful combination formula that's going to come up when we do all of our circular motion problems. And there's going to be a lot of them. The variables themselves are all defined right here. You can see that this is the forces. Anything along this axis would be things that work as our sum of forces. Then we have our tangential velocity, our mass, and our distance from our center of our circle would be our r. So that's the big stuff on circular motion that we need to know. Thank you for watching. I hope that you guys remember these bad words and never ever get caught using them. Thank you. Bye.